Hey guys, welcome back to day 3 for instruction this week. We're going to continue talking about linear correlation and how to run our hypothesis test for linear correlation and using the equation to make predictions. All right. So today we're going to be looking at some data about CO2 and temperature. So one of the big debates today is whether or not the global climate crisis is a real thing. And I'm not gonna tell you whether or not it's a real thing or a fake thing. Mostly statisticians rely on data, right? And the type of data that they collect to confirm whether or not something like that is happening is they compare CO2 levels in the atmosphere and then they compare that to temperature. So on a given day, they might go out, take an atmospheric sample and analyze how much CO2 is in the atmosphere, and then also get a temperature reading to pair along with that. And they'll take thousands and thousands of these readings, right? So what we're looking at is maybe a small chunk of data from a global warming study that might have been done. And we're going to take a look at that and see what we can do with our correlation stuff concerning that particular topic. All right. So the first thing that we want to do is we want to create a scatter plot and look for a linear pattern or any kind of pattern really. It doesn't have to be linear, but for the scope of this class, we're only going to talk about linear correlation. So for our purposes, we're looking for something that is linear. But there are other types of correlation out there. There's quadratic, there's exponential, there's cubic, there's all kinds of different regressions that you can do. All right. So I've got my graph already made here because honestly, creating a scatter plot is just a matter of plotting points, which I know you guys are probably really good at. Some things to keep in mind as you're creating your scatter plot is to make sure that you put a label on each of your axes. All right, I didn't mention that in the last video, but you're going to want to make sure that you label what each of your axes represent. And when you do that, you're essentially picking what is the x variable going to be and what is the y variable going to be. All right. So then you want to make sure that you choose an appropriate scale. All right, so my data only needed to go from 300 to 370. I didn't have to start at 0 here and make this the origin. So this is actually not an origin here. It's just this is the window that I'm going to look at for my graph. All right, so just make sure you do choose an appropriate scale that allows you to kind of spread out a little bit and use most of the graph that is available to you. So you don't want to try and crunch up all your points in a little ball right around here because you didn't choose the appropriate scale. All right. Then you want to make sure you draw in your line of best fit, and that way you can start to judge what the strength of your correlation is, what direction it's going, and things like that. All right, so we do see somewhat of a linear pattern going on here. It looks like as the CO2 amount is going up, it looks like the temperature is going up as well. So we see kind of a positive relationship between the two variables. And if I had to pick a shape here for these points, it looks like it's trying to make a line. So I went ahead and drew in what I thought the line of best fit would be. And I just eyeballed that in there. I didn't actually go and get the equation or anything and graph it. I just kind of put it in there where I thought it should go. All right. And remember that you can do this on your calculator too. So you can go to your calculator and enter in the data. So let's practice doing that. And we'll compare my handmade scatter plot here to the one that we get on the calculator. All right. So let's go to Stat and Edit. And then go ahead and take a couple minutes and input the data from the top of your notes here into L1 and L2. So go ahead and pause the video and do that now. All right. So we should have our data put in there now. So I'm going to check out the scatter plot. And so I'm going to go to second y equals. And I'm going to turn plot 1 on. And then I'm going to make sure that it knows my data is in L1 and L2. And I'm going to make sure that scatter plot is selected. And then before I hit graph, I'm going to go to Stat. And I'm going to go to Calc. And I'm going to do my option 4. And when I do option 4 again, just make sure it knows where the data is. It should be in L1 and L2. And then to get the line on my graph, I'm going to make sure that this says Y1 right here. So I'm going to hit not second, but alpha and then trace. And it'll be option number 1. And it'll store whatever the regression equation is, whatever the equation for the line of best fit is, into Y1, your Y equals button here. So it'll graph that line. Okay. And I'll hit calculate. And initially I'll be able to see what the equation of the line is, and I'll also get my correlation coefficient here, R, and my coefficient of determination, R squared. All right, so 0.892, keep that number in mind for the future here. So let's take a look at our graph. Oh, and make sure you do zoom option 9. It'll automatically fit your window to your data. So there's our graph, and there's our line, and it's looking pretty good compared to what we got here. All right, so two ways, by hand or by calculator. I don't really care how you do it, but you do need to look at the graph and verify that the points are in fact trying to make a line. If you see a clear shape otherwise, then you would not go for a linear correlation, you'd go for something else, all right? That's why it's always important to do step 1, just to kind of get a visual inspection of the data and see what it's doing, right? There we go, we did pretty good there. It's looking like a line. And the first thing they want us to do, if we're looking at our notes here, is they want us to comment on the strength and the direction of the correlation. All right, so if I'm looking at this, most of the points are pretty close to the line, which would indicate a strong correlation, right? So I'm going to say strong. And it's positive, right? Because it's going up and to the right. So this is a positive correlation. And it also wants us to note what the sample linear coefficient is. And remember I said that was 0.892, which further confirms that we might have a strong correlation going on here. Remember, when this number is close to 1, it would indicate a strong correlation, and 0.892 is pretty close to 1. All right, so so the next thing that they want us to do is they actually want us to run the hypothesis test to fully confirm that we have a strong enough linear correlation to be making predictions. All right, so let me get a different pen color here, and we will do exactly that. And to start a hypothesis test, we need to make sure that we have a null and an alternate hypothesis. So I'm going to set up my null and my alternate. And for us, what we're always going to do is we're always going to take the population correlation coefficient, right, which has that weird row symbol, and we're going to set that equal to 0. We're always going to assume our population assumption is that there is no linear correlation, and that's what this equaling 0 means, which means my alternate hypothesis is going to be that it doesn't equal 0. In other words, it's far enough away from 0 for us to not believe this, okay? So then I'm going to go to my calculator, and I'm actually going to run the lin-reg t-test, which we learned about in the last 2 sections of notes. All right, so if you go to stat, go over to test, and we go down to where it says lin-reg t-test. Option F, it's pretty far down there. There it is. And again, tell it where your data is, should be in L1 and L2. And make sure you select the not equal to 0 for the alternate hypothesis. You don't have to do anything with reg EQ, and then just hit calculate. And there we go. So we got our test statistic, and that's one of the things that I want you to write down. I want you to write down what the test statistic is. And in this case, for us, it was 5.58. And then I want you to grab the p-value. So the p-value is the other thing that we need. And if you look at this, it's going to be 5.21 e negative 4. So we'll just say 0 plus. All right. So remember, the t-value here tells us that we are 5.58 standard deviations away from what we assumed about the population, which was we assumed the linear correlation coefficient would be 0. Well, we're 5.58 standard deviations away from that expected value. And the probability of that happening by chance is virtually next to none, which means our assumption about this is probably false, right? So we're going to compare that p-value, that 0 plus, to our level of significance, which is 0.05. And 0 plus is clearly less than 0.05. So this is telling us to reject the null hypothesis. Okay, so we're going to reject the null hypothesis. And if I reject this, then I must accept this. All right, so, and this is the alternate hypothesis where we say, hey, it's not equal to 0, which means we do believe there is a linear correlation between these two things. Okay, Okay? So there is sufficient evidence to support the claim that there is a linear correlation between CO2 and temperature. All right, now in the previous notes, we didn't really pay a whole lot of attention to writing that conclusion statement at the end of the hypothesis test. We were more focused on what was happening over here, but do make sure, use this kind of wording when you're writing that conclusion statement, all right? We always want to say there is sufficient evidence or there is not sufficient evidence, and I always frame it in how we are supporting the claim or we're not supporting the claim, okay? So I would read this and make sure that your conclusion statements are modeled fairly close to what I wrote here. All right. So then we move on to number 4. It says, based on your test, does it make sense to find the linear regression equation? And it does, right? So we established that there's a pretty strong linear correlation with our hypothesis test. So it would make sense to go ahead and find the linear regression equation and use it to make predictions. Okay, and you can grab the linear correlation coefficient from your calculator. They give it to you here where they tell you A and B, and look at the format that they give you. B represents the slope, A represents the y-intercept. Okay, so I'm going to go and write my equations. We're going to say y equals, we're going to say 0.01x plus 10.48. So this becomes a model that we can use to make predictions. So if the CO2 level is this, then the temperature could be this, okay? So that's what we would use this equation to do, and this is how statisticians and mathematicians make their models to try and predict what's going to happen in the future, all right? So let's say we knew that the CO2 saturation was 370.9. What would the best prediction for temperature be? Well, they give us a CO2 reading, and remember CO2 was the x variable, so I'm going to be plugging that in for x. I'm going to say y equals 0.01 times 370.9 plus 10.48, and then I would crunch that number. And what I get out after I crunch this calculation is the y value, which is our temperature reading. Okay, so I'm going to go here and I'm going to crunch that in my calculator real quick. I got 0.01 times 370.9 plus 10.48. And we get a temperature reading of 14.189 degrees Celsius. Right? So 14.189 degrees Celsius. Okay? So that's how we use it. That's kind of the gamut of using linear correlation within the scope of this class. There's many other ways that you could use different types of correlation, and there's other correlation methods as well that are out there. But this is just an introduction to it. So let's talk real quick about some of the common errors when using correlation, and these are very important. Especially the first one. This is something that I'm telling you right now. I will put something about this on the final exam. One thing that you need to make sure you understand is that correlation is not the same thing as causation. So for the example that we just did, okay, we talked about global warming and the relationship between CO2 and temperature. Okay, and what we established in our test was that there is a correlation between those two variables. In other words, when the CO2 levels go up, so does the temperature. But that is not the same thing as saying that CO2 causes the temperatures to rise. There's a difference between correlation and causation. I can say they're correlated, but I can't say that one causes the other. A good example of this is to think about the number of drowning deaths and temperatures outside. Okay, so you'll notice if you ever look at the data between drowning deaths and temperatures, is that the drowning deaths go up as the temperature outside rises. And that kind of makes sense, right? Because as it gets hotter outside, more people are going to go swimming. And when more people go swimming, they drown, right? You'll have more drowning deaths, okay? So we can say that they're correlated, but it would be silly to say that just because it's hot outside, that's going to cause you to drown. Right, so there's a big difference between correlation and causation, and you need to make sure that you watch out for that. Okay, so if you see something on your final or on the test that's like, hey, this thing causes this thing, right? Look for the word causes, right? instead of correlates. If you see this and you know that the statement is false, we can't establish causation using correlation techniques. Okay. Number two, most common error, many beginning students will assume that there is no correlation because there is no linear correlation. Most statistics classes start off examining linear correlation, so that's typically all students see if they don't take any more of the advanced courses. So they'll assume that there is no correlation between two variables if they don't see a line forming. All right, but there are many other shapes out there, quadratics and exponential correlations, the cubic correlations, like I said before. This is why we visually inspect the scatter plot. So we don't want to say that two things are not correlated, especially if they're making another distinct shape besides a line. All right. And then the number three most common error is people try and use their model beyond its scope. Okay. An example of this might be taking CO2 and temperature readings from 1900 and trying to use that data and the model from that data to make predictions about our year 2020. And things were much different back in 1900 than they are in 2020, and trying to use a model that's 100 years old is probably not going to be accurate or precise by any means. Okay, so your data has to be updated. It has to be somewhat close to what you are predicting. So if your data comes from 2020, you don't want to be making predictions for 100 years from now. You might want to keep that prediction in 5 years or 10 years from now. All right. That's why a lot of people get upset when they see models predicting what's going to happen to the world as a result of global climate change 100 years from now using data from today. All right, so that's one of the things with studies today that people have a problem with. All right, so let's continue on. We're going to do one more example here. We're going to take a look. You might remember this example from the beginning of the semester. We're going to take a look at chirps per minute of a cricket and temperature. There was a very famous study a long time ago where the connection between how crickets chirp and the temperature outside, they discovered that these two things are in fact related. So it's kind of a weird thing. You can actually go outside, listen to the crickets, and you can determine or make a prediction about how hot it is. Okay, so and I do believe these are not Celsius, these are in Fahrenheit, so that's a typo on my part. All right. So what I would do is go ahead and get this data entered into your calculator, and we'll try and do as much of this on the calculator as possible so we can get through it quickly. All right, so go ahead and take a minute and put this into L1 and L2. All right, guys, hopefully you have your data entered into your calculator here in L1 and L2. So just like last time, the first thing I'm going to do is I'm going to go and turn my scatter plot on, just make sure everything's set up for that. And it should already be turned on from your last problem, and it should already have L1 and L2 selected for your X and Y list, and you already should have scatter plot selected here. Okay, but if you need to change any of those, go ahead. Before I go to the graph though, I also like to run my linear regression. So I go to stat and then calc, and then I like to go to option 4 and make sure it says L1, L2, and I'm going to go ahead and store the regression equation so that I can see the line at the same time. All right, so alpha, trace, option 1, and calculate. The first thing I notice, that correlation coefficient being 0.87 indicates a strong positive relationship, but let's also look at the graph. I'm going to hit zoom and then option 9, and let's see what we got. So visual inspection here shows definitely a linear correlation with the points. I can see these points kind of wrapping around this line. None of them are too far away. So we're looking at a pretty good, strong linear relationship here that is moving in a positive direction. So I'm going to say over here, this is a strong correlation and it's positive. So that is my comment on the strength and direction of the correlation. And our correlation coefficient, I forgot the number, I think it was 0.89. Darn it, I'm going to have to run it again. 4. Calculate. There we go. And we got our correlation coefficient of 0.874. So I'm thinking when we run our hypothesis test here, we should end up rejecting the null hypothesis and agreeing that there's going to be a significant linear correlation here. So let's go ahead and set that up, right? Hypothesis test. right? We're going to say that rho is equal to 0 in the null. We'll say that rho is not equal to 0 in the alternate hypothesis. And then I'll go ahead and run that linreg t-test. So you got to hit stat, go over to tests, and it's going to be option F way down at the bottom. There it is. Hit enter. And make sure everything's selected here, L1 and L2 for your X and Y values. Be not equal to 0 should be selected, and then go on down to calculate. So we got a t-value, that's what we want, that's our test statistic, 4.39. We'll say 4.40 for rounding. Okay, so we were 4.4 standard deviations away, which is a pretty difficult thing to do. And our p-value, bet you is 0 plus, oh, not quite, so we'll say 0.005. And so this is the probability of getting this test statistic by random chance, assuming that this is true. So that's virtually impossible. So this cannot be true, which means we are going to accept this, right? So if I compare my p-value 0.005 to the significance level of 0.05, it's definitely less than, which would mean that we reject our null hypothesis and accept our alternate. Okay, so there is sufficient evidence to support the claim that and I should say significant linear correlation exists between chirps and temperature. Okay. So does it make sense to find the linear regression equation? It does, because we can use that linear regression equation to make predictions about the temperature, which is ultimately why we are doing this. Okay. So we're going to say our slope is 0.052, so I'm going to say y equals 0.052x plus, and I'll go back and get my y-intercept, which was the a value, so it's 27.63. So there is my equation that I can use to make predictions, and let's see what prediction they want us to make for this. If we knew that the number of chirps was 3,000, right, so 3,000 chirps per minute, I'm going to take that 3,000, I'm going to be plugging it in right here where the x is. So let's see what we get. 0.052 times 3,000 plus 27.63. And I got my calculator here. I got 183.63. There we go. Would be 183.63 degrees Fahrenheit, which is really hot. So this makes me think a little bit. This is this isn't a weird prediction. I've never seen it be 183.63 degrees outside, at least not where crickets live. So I'm wondering if maybe this data point that they gave us, maybe this 3,000 chirps per minute, is a little bit outside the scope of our data. And I'm looking at the chirps per minute from the original data set. You notice how nothing is close to 3,000 at all? Okay, so the number 3,000 is well outside the scope data that we were using, which means it's probably not going to make an accurate prediction for temperature, right? And that's kind of what we saw when we used it, is we got to predict a temperature of 183 degrees, which, you know, I don't know that any point on Earth has ever reached that temperature, you know, at least not in our day and age. So this would not be realistic. I think this is beyond the scope, right, of our original data, right? So that illustrates that common error number 3 that I was talking about before, right? Everything worked out, but at the end we realized, hey, what the prediction they're asking us to make is not something that we could use our data for, all right? All right, guys, that's it for this week. Good luck on the homework. If you have questions about anything that you see on there, make sure you email me, schedule an appointment, get some help. You know, do your best. And this is the last week for content, so the light is at the end of the tunnel. Finish strong and get your college credit, all right? Have a great day, guys.